All right, today we're going to talk about power. Power is the rate at which work is done. So, we have talked about work. We know that work is done by an external force outside of whatever system we're using. That external force is applied over some distance and work is done. Now that could be me pushing a box, so I'm applying a force over a distance as the box moves. And I am adding energy into that system. I am not a part of the box's system. So if the system for the box is just the box, my work would be turning into kinetic energy. If I push the box up a ramp, then my work would be turning into gravitational potential energy. If I push the box against a spring, my work is turning into spring potential energy. Either way, I am adding energy to the box's system. I am an external force doing work by applying a force over a distance. We learned about work. We know there are 4 conditions. We know that for work to be done, the force has to be applied over a distance, so it has to move. We know that that distance and the force must be pointed in the same direction. They have to be parallel for them to do work. We know that the work is positive if the force and distance are in the exact same direction. It's negative if they are in opposite directions. And there would be no work done at all if they're perpendicular to each other. So we know about work. Power uses this term rate. Rate should always remind you of time. It's how much work is being done in a certain amount of time. And that's the definition of power. Power is equal to work divided by time. The units for power are going to be watts, which are equal to joules per second. Work is in joules, time is in seconds. So power is the rate at which I get work done, okay? So let's talk about Tom and Fred. Tom raises 10 kilograms of stuff 3 meters in 10 seconds. Fred raises 30 kilograms of stuff 10 meters in 30 seconds. Who has more power? So we're going to compare the average power of Tom and of Fred and see who has more power. So when we look at this equation, power is equal to work over time. Occasionally we'll modify it and say we can also think of this. We know work is equal to force times distance. So another way to write this same equation is force times distance divided by time. So for Tom does, what is his force, right? Let's think about it. Tom's applying the normal force to all this stuff that he's raising up. So he's applying a force of 10 times 9.8, so 98 newtons. The distance he's covering is 3 meters, and he did it in a time of 10 seconds. So Tom's power would be 98 times 3 over 10. I'm going to roughly round that to be 3 watts. For Fred, he's applying the normal force as well, assuming that's equal to mg, which we are therefore making the assumption it's moving at constant speed. I'll show you another way we get this work component. We split it into force times distance. I'll show you another way to get it using just maybe a conservation of energy equation, which can also work in a second. And I'll prove to you that even if it wasn't at constant velocity, this actually still works. I'll show that in a second. So if the force is equal to Fn, I have a weight of 30 times 9.8, which is, I'm doing maths, 294. The distance it traveled was 10 meters, and Fred did it in a time of 30 seconds. So his power is equal to 294 times 10 over 30 seconds. That works out to be 9.8 watts. So, even though Fred took longer to do his work, he actually did a lot more work. He did a substantially larger amount of work, 2,940 joules of work. So even though it took him longer, he actually had more power. Now, I mentioned that we could solve this for the work portion using force and distance, but another way we could have done it was to say this. We could also say that what was Tom's box's conservation of energy equation? Tom's box started at rest on the floor, so it started with 0 energy. Tom did work to it, added energy into the system, and then all of that energy, he put it on some shelf 3 meters high, so all of that energy turned into gravitational potential, mgh. So the work Tom did would be equal to the mass, 10 kilograms, times g, times the height, he lifted it. Notice that's the exact same thing as what we had here. The reason that technically works is because whether I lift something up at constant velocity or I really accelerate it, either way, it averages out to an average velocity of the distance that it traveled over a certain amount of time. That average velocity is true no matter whether I accelerate it up or moved at constant velocity. That average velocity is actually what this power function is looking at. And so since I speed it up and it's going really fast, but then I have to slow it down to get it to the top, there are parts of it where it's accelerating positively, accelerating negatively, moving at constant velocity. So you can make this assumption that the force is equal to Fn, because I'm lifting the object, and that's equal to Fg, because on average, over the time that I lifted it up, it is. The average velocity was the same, distance over time. So much so, the fact that power uses average velocity is really important because I notice that average velocity is in the equation. Distance divided by time is average velocity. So a third way I can write this equation is force times velocity. Distance over time is equal to velocity, so I get force times velocity. And we really love to use this equation here. It's actually one of our favorites. So let's see what that could possibly look like. So we have force times velocity. Again, this could be as simple as I say I'm applying 100 Newton force to this while it's moving at a constant velocity of 20 meters per second. What is my average power? That's an easy one to do. So I can just plug force and velocity in. What if we wanted to make it a little bit trickier? Let's say this. I have 2 ramps. One is steeper. One is flatter. But they both go up a height of h. No matter how I drew them, they both go up the same height. So I have 2 ramps, one is steeper, one is flatter. And I'm going to push an object up both ramps at a constant velocity v. So both ramps, I'm going to push it up a constant velocity v. That's the same for each. So I want to know which ramp requires more power to push this up. You might be thinking to yourself, well, the work done to get to the top is the same. right? Both of these boxes started with 0 energy at the bottom. I'm going to push them to the top of the ramp. They're both the same height, so they'll have the same gravitational potential energy. So shouldn't the power be the same? Well, no, because I'm not going to get up there. I'm going to get up there in the same amount of time, but I'm going to have done different amounts of work. And here's why. Remember, the force to push this up the hill at some constant velocity v, if I draw the free body diagram for a ramp, it's mg cosine theta going down, Fn going up, some friction going down the ramp because I'm pushing it up, and then my force of push going up the ramp. So my force of push must be equal to the force of friction. So that means my force of push must be equal to mu mg cosine theta. So the power it's going to take for me to push this up is equal to force times velocity. So my force is mu mg cosine theta, and my velocity is v. And here's where the difference is. On the steep hill, this theta is going to be really, really large. That theta is going to be really, really big. Oh, I'm missing a component too. I'm also missing, going down also is some mg sine theta. So my force of push is also plus mg sine theta. Whoops, forgot about that guy. Mg sine theta, mg sine theta. V. So as the angle gets steeper, it's going to require more force to push it up. Even though they're moving at the same velocity, it's going to take more power to push it up the steeper hill than it will be for the lower hill because of those thetas that are in there, right? Mu cosine theta plus sine theta is going to get bigger as the angle increases, right? Because this number gets smaller by a smaller amount than this number gets bigger. So something to consider. That's a little bit of a trickier, maybe AP style question. Let's do one more thing here. I want to know, this is also a tricky question. I have a box pushed on a horizontal surface. So that it accelerates at a constant rate. Derive an equation for the average power to move the box a distance d. So, again, something we've been highlighting in class, and we'll do that in the video as well, is that problem-solving thought process. So I'm looking at this. I have a box pushed on a horizontal surface so that it accelerates at a constant rate. Derive an equation for the average power to move the box a distance d. Let me make sure the question doesn't have anything else, because I feel like you need one more thing. D in time t. Yeah, I knew I forgot something. In time t. To move the box a distance d in the time t. So I want to know what the average power is for this. So, things that I know, I'm accelerating at a constant rate. So my average velocity can be said to be equal to v naught plus v final divided by 2. Well, I know that the v initial is 0, but I don't know what v final is. That's unfortunate. I don't know what v final is. But I'm accelerating at some constant rate A. Some constant acceleration A. I also know that I traveled a distance d in a time t. So that's all the information that I have. And there are lots of ways that I can solve this. I'm looking for average power. So I could do work over time, so FD over T, or I could use FV average. Either of these will work. So the question is, which one is best? So FD over T, right? I have D and I have T and I have a way to get F. F would be equal to mass times the acceleration, right? That's a way to get that, mass times the acceleration. Well, what is mass times the acceleration? What's that acceleration? I don't know what this is. Sorry, I put an A, but I meant to put a question mark. So let's think of all the things that we know. We know V average is equal to V naught plus V final, which we don't know, over 2. We also know that V average is equal to D over T. So let's use that. We know that now VF over 2 is equal to D over T. That's helpful. So VF is equal to 2D over T. That's cool. That's a helpful thing. I know that. Now I can write out that VF is equal to 2D over T. That's helpful. So then we could find maybe some acceleration. We have initial velocity, final velocity, distance, and time. So you could use any of the 3 kinematic equations. The simplest one is always number 1. So let's try that one. V final is equal to V initial plus acceleration times time. So we know V final is 2D over T. V naught is 0 plus acceleration times time. So if I divide by time, I get that acceleration is equal to 2D over T squared. Hey, now I have acceleration. 2D over T squared. That's really helpful. I've got it in terms of some of the stuff that I know. So let's write out a final answer using this equation right here. The force would be equal to the mass times the acceleration times distance over time. That acceleration we know is 2D over T squared times D over T. If I simplify that, I get 2md squared over T cubed. That would be the average power for this box as it's pushed and going at a constant acceleration. Think about the problem solving we did here. Would you be able to do that? Connect all of these pieces. If your first instinct is whoa, 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 no, no, no. Okay, something to always remember in the back of your head from kinematics that's like really stuck in there, but you might have to use a lot when you're not thinking about it, is this V average. If it's at constant acceleration, this is a true statement and can be really helpful to help you find acceleration or a final velocity or all sorts of things. So that's probably the one trick that I see most common in a mechanics class, whether it's 1 or C, is this being used to help you solve the problem. You don't think that you have it. It's the key thing that you needed to connect all of these pieces, and it's something you don't think about. So I would write it down in my notes and say, this is something I should use anytime it says constant acceleration, and I think I might need it. All right, that's all I have. Have a good day.